Hello, everyone. I hope you can hear me. Those of you joining online, please let me know in the chat. I would say in the chat in the Google Classroom that you can hear me well. So just a second, type in question in Google Classroom. Maybe we need a little bit louder signal. I will make it as loud as I can. So in the stream, so I will show you what I mean by that. So here, so can you hear and see me well? So those of you joining online, those of you joining on the class, the little bit more privilege of asking questions and direct help. Others a little bit less privilege, but please let me know in the chat here that you're live and tracking. And meanwhile, I will help out those that are in the classroom. Okay, so I will check what we have in the chat here. Okay, so everything's good. Thanks. So those who are on the classroom, they're on the in-person will have a little bit more privilege, but I will do my best so that everybody can get along. So yeah, so this is the project that we're gonna build today. So the plan will be quite intensive work. So the plan is to go to the numerical library Numpy plus also the linear algebra and some of the equations necessary for the later work. So I will try to demonstrate what actually will look like the end result. So here is one version of it. So I will try to run it first and then make a full screen of it. So where is my full screen? Oh no, there's funny thing that this is gravity game and those kind of So the planets are kind of like having a gravity effect on the spaceship, and it's sucking in. And then when you press spacebar, it shoots out these small exhausts, right? And you can fly towards the planets like this, and it's giving these particles. And so you can make your own game a little bit different from this. It's just that the idea how it works. So and then if we go very close to those planets, they will start to suck us in with gravity. And everything that you see here is drawn by simply by vector math, vector graphs, and linear transformations. And so yeah, it sucked me in here, and then I lose the game. So that's what we have here. Let me go back to Jamboard. That will be the end result. There will be a lot of equations in between. You will need the PyCharm environment. It will not be good today to work with the Google Colab. So you must have either PyCharm or VS Code or something like that, or Spider, or some environment that you can work with. Otherwise, it will not work correctly on Google Colab using this interactive mode. So that's what we have here. Let me think. So I will open the template for you. So please try to get the template as soon as possible. We'll get, so the code template 2.2 will be open now. 2.2 code template. Please make sure that you can run it on your environment. And I will ask a question for this. So is 2.2 template running in your ID? If there is any problem, so plus, minus if there is problems, and if there is problems, then submit a screenshot of what you have there, or code, or the exception. I will try to help you out basically if you have any problems. So please let me know if the template is running in here in the chat. Thank you for those 6 that were responding to previous question. Meanwhile, for those of you who can succeed with this faster, I will give a small small information here regarding the results of the homework. And then we will also look at some of the failures, the homework, to help you out a little bit. But let's first, so you have 2 tasks now. First of all, make sure the template is running, and then you can check out what I have here on the slide. So this is the scores right now for the course. So we see that Elina, Guntis, Martins are excellent now. Others are not so good. And my big warning is that if you will not submit these works in timely manner, you will see today that there will be a huge amount of equations need to be implemented. And basically, the longer you wait, the harder it will be at the end. And I will also not guarantee that I will mark them in a timely manner if you submit it very late. So that's one thing. But I'm very happy for those in top. There is also one big warning. So I saw that Guntis and Dontatas had the same exact code with same exact mistakes. So if I will see that again, there will be 0 marking for both of you if you submit the same code to like multiple students, especially if there is such an obvious like way that they are same. Also, so even if you didn't share the code with each other, if you just Google it and copy it from Google from the same source, it will also get you 0. So please do not do that. So never look for Google or try to copy from each other. So that's so here the 2.2 template. So let me know in the chat if you're ready. Then we will proceed. So. subscribe. So let me know. Let me tell you a few other things. So first of all, like if you have any difficulties of doing the homeworks or the other like tasks and the like making very life or very difficult, please then submit the tasks as well as you understand. So if they are not working, then just submit what you have there. And it will be very helpful for me because then I can explain what those parts that will not work for you. Just code what you can and submit it as a task. That is very important part. The another thing is I will add here now and also later in the materials in the classwork, or maybe I can do it later, but let me try to do that now as well. So I have a couple of YouTube series with also with templates in the same style as this, where we go from very beginning, very slowly how to do anything in Python. So that should be like hopefully very useful for those who are not familiar with programming in Python. So let me try to find. So there will be the playlist in my channel. So it's called Programming for Beginners. Games for to real life use cases, and there is I think 8 tutorial sessions or 7 tutorial sessions for how to do basic things in Python. So that is really recommended for those of you who have any problems with Python. So let me type in here. So basic course in Python if you have any problems with that, please do this very quickly. So I know that this will take a lot of time, but basically, if you want to succeed in this class, you will need to, unfortunately, invest time here. So even if at the end that will not be your specialty, at least you can get past this course if you can do the basics and if you can submit the half working code. So I see that now we have 4 people confirming that you're ready to work, but we are more than 4. So I see in the live. Okay, we actually see that some people are posting in the live. So please post in the same place in the Google Classroom. Otherwise, it's kind of, I don't know which one is completing which. So Donatas, Liga, Elina, Liga, Vipin, and Rohit, I guess. So we have 6 people around. So I will make sure that people in the classroom in person can run everything, and then we will start. So we have so most of you hopefully are ready to work, at least in the in person. They are ready, and also I've seen that in the Google Classroom there is some response that you're ready. Okay, so let's do then some of the first things first. So first of all, I will. Okay, before that, let's talk about a little bit of the homework where there was some issues, and then we will go over the code of today, like step by step, and then we will have a first task actually to do today. You will have to do it yourself immediately. So okay, let me share the screen of the code, and okay, let's actually first look at the task that we had. Okay, so the task. Okay, this is the task. So what you had to do is to create this structure of UML code. Most of you did pretty good of doing these arrows of white arrows, which are the inheritance. That was fine. Some of you had problems with member variables. So the syntax, how to write that in Python. Then also some of you had problems with the composition. So the composition is basically just only what it means is that you have the instance of an object inside as a member variable another object. And those of you who submitted, they mostly got it right about the aggregation, that there are multiple instances of those objects inside another member variable. But let me show you now in the code what was a little bit tricky for some of you. So there is one student who submitted. So this is also a reason why you should submit non-working code as well. If you cannot get it done, then I can explain it. So here there is the way how one person made this class. So this class is made in an incorrect manner. So so the Python way how you write the class member variables is really tricky and not nice at all. So but you need to get along with it. So first of all, let me show what is wrong here. So if I have a position, you don't need to write this. It's just you need to follow it and understand it. So this is from one of the students' work. So you have position A and position B, and you expect that you set some kind of position A to, let's say, x 10 and a y. By the way, this code is wrong, so if you type it, don't do that. So if you type it a and y 10, and then type here bx is 20 and by is 20, and then if we want to, by the way, it's probably you would like to use the setters and getters. So let's use setters and getters. So set as that, and then set as that. Right, so let's do that. And then here, let's change it to the setters and getters, B2020. And then let's write out what we will get here as A, get Y, B, get X. So A get X and B get X. So X from one and X from other. So let me ask in the chat now, what do you think, what will be the answer here? Just to check what others think. So here in the chat, I will drop the question. So yeah, if you go in the Google Classroom stream, you will see this last line as a question there. So please type in the wall. Okay, I see that I have somebody asking me also, anyone have any idea why on top replica freeze when window gets minimized? Yes, unfortunately, Windows have a lot of issues. Microsoft in general have a huge number of issues. So what you need to do is make sure that the window that you replicate on top replica is not covered by another window using maximized function. So you need to make sure that the window is kind of like reduced in some with a small like a border around it. It's like Windows is kind of optimizing if something is maximized over another window, then it doesn't render it at all. So please, hopefully that makes sense. So I will write that in the chat as well. So make sure window that you are replicating is not covered by another window with maximize option, and also you cannot duplicate anything that is minimized. Cannot duplicate anything that is minimized. So those two things. Okay. Yeah. So and yeah, question in the chat. Still nobody. Oh, somebody answered. Okay. So Martin's answered. Let's wait for other people. I'm showing the code on the screen now, but the question is actually in the Google Classroom. Let me show what I mean by that. So if you go in Google Classroom, here I have the question. I'm waiting for the answers. And here is the code itself. So please let me know in the chat. I'm waiting for that. So I see 2 answers, still waiting for more. Hopefully my question regarding the on-top replica was sufficient. I mean the answer. So yeah, meanwhile, I will add the material or the Python basics inside our Google Classroom. On top of that, so playlist with Python basic tutorials. Complete this if you have problems with Python. So that will be available for later. And I guess if you have the problems now, then it means that till the next week you need to complete that, plus also the other things that we are right now doing. So let's see. Okay, so I have some of the answers. So most of you saying 10 and 20. So let's double check. Exit. So yeah, right, run. And we will see that it's 10 and 20. Maybe I myself did mistake. Haha. That is funny. That is funny. There's something going on. Okay, you're right. But let's see why I was suspicious about this code. So let's see. Okay, it works. That is a little bit of surprise for me, because normally this way we define static variables. Okay, that is surprising. Anyway, yeah. That's interesting. So let me check it what happens. But this shouldn't make changes anything. So this is interesting because some time ago at least this was the way how you define static variables in Python. So yeah, let me quickly double check this thing. That's the, I even did not run it. I just looked at it and I know that is a static variable, but then it doesn't behave like static variable. So if somebody knows what's happening here, why it's not behaving as static variable, you can maybe type in the Google Classroom wall. Meanwhile, I will quickly check what's happening here, because this is really strange. Definitely should be a static variable. What do you mean AX and BX? Okay, let's see. But still, I would be surprised if it makes it different, because the pointer should be on the same place. Yeah, so it's not different there, but it's might be. Let me check what kind of Python version do I'm running or something. Okay, this is surprising for me. So I guess I will update the mark for the student who did this, because on at least on Python 3.9 works in this manner. Maybe they changed something. Let me check, which is very strange. I will check the Google Classroom also in a second. So let me try to run it on 3.6 Python. I'm trying to run it now on 3.6. So run. Okay, this is 3.6. Yeah, it works the same way. So there's something going on, which so I consider myself knowing the Python pretty well. There's a lot of caveats there, but well, maybe that's related. No, yeah, let's check what about. Couldn't be that, but maybe it could. So let's see. Well, but no, this is not the case. This is definitely not the case. Okay, let me check in the chat. Maybe somebody knows the answer. What is happening here? Okay, nobody wrote about the stat. So normally, this is the way how you define the static variables, not the not just the like the member variables. We'll quickly check this and then we will move on. What I'm missing here. Okay, let me check. So one way, if this would be a static variable, I could do something like this. Let's try out. So 30. So it should. Oh, it's not. No, it is working like static variable. So then if I run it, now I still get it as now non-static variable. Yeah, maybe. Yeah, let's check what's there, what's inside there. Actually, with the breakpoint. Okay, this is unexpected. Mm-hmm. Yeah, yeah, yeah. Let's add some kind of more experiments. So main test. So I did B main not test A in B main run. Yeah, this is super strange. Okay, so I will. Yeah, yeah, but the data types are actually not enforced. So that's also a good point here. The data types here, it doesn't matter at all. They are just for the just for your uses. Yeah, yeah, that's because I use here the integer, so that's why. But that's not a problem at all. So what I was trying to show you is that there is a way how to define static variables, which they should be in that way. Really, really at this moment. So let's forget about this. This is not important now. I will check till the next time, or somebody else can help me out in the chat. What's happening there? Because there should be the way to define this is normally if this is a static variable, static. So I'm not sure exactly how this could happen. Object. Well, maybe we should. Maybe that's because it's not calling the constructor. I don't know. So let me see. So maybe we will discover some new thing about the Python that I myself didn't know. So let's see. So if I run it with a constructor, let me see what happens. Okay, it's still behaving in the same manner. It should be static there. Okay, I will not waste time with this more, but so anyways, the student who did this basically did it, I guess, correctly with the way how the Python works. I will need to double check it. But in general, there is a thing called static member variables. I will make sure that I find what is the difference here and give you the examples next time. So let's move back to the code. We already lost a little bit of time because of this unsurprising event. So anyways, so if I run the game now, what we get here is following. I will show you. By the way, I will keep looking about that static variable while you will do the class works today, because it should be not difficult to find what is happening there. So I will share the full screen, and it looks, so the game looks like this. So it's not, and if you press escape button, it goes back to the normal. Okay, so that's what we have. Then for the first task, so I will first go to the code. So here in the top part, we have the defining of what what will be the matplotlib interactive mode. So that means that we have a graph environment, the visual environment, that is able to refresh after we run it. It's not just rendering the graph once. So, and that in my case, I will use this backend. You can choose which backend you want. Then here we have some functions, mathematical functions that we will implement today. Also some functions here, some functions here. Then we have a couple of classes. So movable object. In the game, we will have multiple movable objects. So there we have the geometry. So this is the spaceship or the planet or so on. Then we have some of the transformation matrices, combined transformation matrices, rotation, scaling. So that's what it means. So maybe if you want, you can add comments. So this is combined, combined. This is rotation. This is scaling. And by the way, there could be multiple scaling and rotation matrices. So then there is the position of this object. So this, what it actually means, MP0 by shape of 2, that means that the position by default is this 0, 0. So this function generates this vector. We can even write it in that way. So either using the this way, or we can just write it like that. It will be exactly equal output. So like that. Then the direction is necessary to calculate the rotation matrix based on the angle. So now direction points upwards. So up is plus, down is minus, left is minus, right is plus. So I can even write it down. So top is -1, top direction down. So let me say up. So sorry, up is 1, down is minus, left is minus, right is +1. So these are the directions of the plot, and the middle of the plot is the center of the screen. So then we have a copy of this vector. So initial vector is copied here in the other vector. Remember that pointers do not work like this. If I just write it like this and then change this direction, I will have very bad consequences because it will change automatically also these values. So we need to copy it, and one way is using another NP array. Other way is to use, I think there was a function clone or copy. Yeah, so we can use also a copy function like that. Then the external forces, so that is, there will be multiple planets, and this is actually matrix here. And the matrix looks like this. So we have one row, and in one row we have 0, 0, like that. So that is like our very simple matrix, two-dimensional here. You can also, of course, write exactly the same thing as this using this syntax, NP array. So 0.0, so like that. So this is exactly the same code as one above. It's just different way how to write it. So this is shorter. So you will need to work a lot with shapes very soon. So there is the shape of the matrix. First number means the rows. Second number means the columns. So that is what we have here. Then we have set angle. So all of the objects in the game can be rotated. So we will rotate this object with some angle. We will calculate rotation matrix here. Then we will convert from two-dimensional vector to three-dimensional vector because the so I think, what was it, translation, or I think it was rotation. So yeah, so around the z-axis, rotation requires us to have, or yeah, was it rotation? Just, I think it was rotation. Around the z-axis, rotation requires us to have 3 dimensions. Just don't want to tell something wrong. Let me check. Was it? Yeah, I think it was z-axis rotation. So let me see. Okay, no, it was translation around z-axis. So where's the translation? Yeah, so the translation around z-axis, requires us to, from the top side, so it requires us to have the third dimension. That's why we have 3 dimensions. So you will see that in a second. No worries. So the 3-dimensional thing is not always necessary, but in this case, it will help us to combine all of the transformation matrices in one matrix. So okay, I still don't see any comments in the chat so far. Okay, so then we will update the transformation matrix, so that will be the combined one. Then we will go to the geometry and draw one by one each 2-dimensional vector and add it to the plot. So we will have the x-axis and y-axis. Then we have the player. The player is the child class of movable object, and the player has the original geometry here. Then we also change the position of the player to -7, -7, so it's not in the center anymore. And then we will do some things with the player. So then when we create an instance of a player, we add it to the actors list. And here we have some of the interaction functions. So first of all, the function for pressing the keyboard buttons. So here there is the connection with the keyboard. And now if we press escape button, we set is running false. If we press right or left button, there is a to-do modify angle -5 or +5 degrees. And so that we should do. And then if we close the plot, it will also stop game. And here is the main game loop. So this is the main game loop, And in this, with the 0.001 second interval, we redraw the game. And here in this part, what I want you to do is add the angle of the player as a title of the plot here. So what I mean by that is following. So we are drawing the game here, and let's add another line here. Plot title, and here print angle of player here. So let's see what happens if I run it. Okay, let's see if it adds the title. I think it actually didn't add me the title. Okay, I know why, because it's out of the box. Okay, let's do it in a different way. So plot box annotation box annotate. Let me find the way. So the text and then the position. XY, just a second, print, I will update probably this, so let's see, so XY, let's see what will happen if I add it in 0.0. Okay, let's see what happens. Okay, print angle here, so it's in that part, so that's not perfect. -10, -10. It should be in the top part now. Okay, that's too far. -9, -9. Now it will be good, I think. -9. Okay, yeah, so now it's in the bottom part actually. So I will show you the screen, what it looks like. So it looks like full screen like this. We have the small text in the bottom part, print angle player here. You will have the same thing now. So I will go back to the code. Please do this line here, and then I will open the first task. So the first task for you will be to actually print the player angle here using the keyboard buttons, changing it by 5 degrees in both directions, and make sure that it's changed actually by printing it out on the plot. So is the task clear or not? So first of all, I will add it in the Jamboard, and then I've asked that question, so is it clear or not? So let me add the example of how to do that. You actually need to change only very little in the code. very little in the code. So the task is 2.3. 2.3 task. It's open now. We'll make sure that I update the example. Okay, so the stream. Let me ask in the stream now. Is the task 2.3 clear? So what I want you to do is to write in that line the angle of player while it's turning. Basically, I will quickly maybe write that code and show you what it should look like. Not the code, of course, but how it behaves. So So the code should behave like this. If I press button, then you see the angle value decreases. If I press one button, if I press another button, it increases by 5 degrees, like that. And the player is not turning actually right now because it's not implemented yet, but we can change the scalar value of the angle here. And you can display it on the plot in that annotate box. So you already have all the pieces necessary to do this, so please do it. If any questions how to do that, please ask in the Google Classroom, or I can help you out also here on the in person. So just a second. This should be a very basic task. If you are okay with Python, if you're not okay with Python, maybe it's difficult. So I understand that. Let me see if somebody handed in. Nobody yet finished the tasks. Kā ir tā rindiņa jau pieejama kodam, ar kuras palīdzību, nu, es viņu tur ielicu tajā uzdevumā, 2, 3 iekšā. Es parādīšu uz sienas arī. Rekur, šī ir tā rindiņa. This is the line where you need to print out the player angle, and these two lines are that you need to change to modify the angle. Kādā mātim izdodas uzstāt? Let me see in the Google Classroom. Nobody yet finished this one. jābūt tikai kā naudas vai satālumā, kas nestrādā, no tādiem ir ļoti svarīgi modeļi. Un šajā veidā ierakstā to uzzīmē to tekstu, lauku. Un šajā veidā kas ir slēdziens laikas, šeit ir kādā laikas. Bet, nu, ok, es jums tāpat parādīšu pēc brīža, kā to izdarīt, bet vismaz uzrakst to anotēt daļu. Okay, I actually don't see a response on the question, is the task 2.3 clear? I suspect that you understand it and you're doing it now. If there are any problems, then feel free to write in the Google Classroom, like either screenshots, errors, questions. I will try to respond as fast as possible. Also, those in person in the class, I'm ready to help. Sorry? Push. It's open to action. So, seems like, okay, don't really know how to modify angle. Thank you for the question. I will show. Will show, no problem. So just let's see if I want to check like how well you understand code so far. You'll see Martins in the class in person says that he has done the work, but is not yet submitted. We'll see if somebody else also can submit it. Try first yourself, and then I will try to show you. But basically, if you submit the first in the Google Classroom, I would be very happy. Let me see what we have in the Google Classroom. So the only one, I guess, who submitted is the Martins, which is surprising in my opinion, because I know in this course there are a few other people who are capable of doing this. Okay, so that's good job, Martins, and I'll give you immediately the score for this. Plus also recognize you in the Google Classroom. So there's the Google Classroom thing. Okay. Elena also submitted the task. Let me check if Elena's work also works. So Elena's task also good. Also good. So Elena and Martins did this correctly. So, okay, but I will show you in a second as well. Okay, cool. Liga also, I guess, got it. Yes, yes, we need to modify the. So, but Elena already got it. So, Elena and Martins will get a cookie. So that is good job. So, good job for this. And I will show you how to do this now. So here, in the, as some of you asked in the chat, yes, you need to modify the angle here in this function player. So set angle, and this case we take, so we can even write it in separate lines, because also that was one thing that I saw in the homework. Some of you write the code in one line. So if you write the spaghetti code, it's very dangerous. So let's write it in multiple lines. So angle, player, uh, uh, get angle, and here I wanted to actually set angle, and the angle minus, so we could actually write it in separate line, angle minus 5. Of course, I can write all of this code in one line. The only difference is that, of course, this is super simple code. There's no problem of writing that in one line. But as long as the code is simple, it's good. But when the code will become harder, like then this kind of way of splitting the execution in 3 lines is much better, because now I can add the breakpoints here, check the answers, even the operator of -5. This operator can also do interesting things, like if it's a Numpy operator, it can remove that value from all of the vector items. So it's just good practice of trying to write your code in multiple lines rather than writing in spaghetti code. So here, +5, so we are adding the angle. I will drop this into Jamboard now as well. So for those of you who want to catch up with this, I will not do this all the time. I'm just like helping you out in the very beginning now, as I understand that it might be a little bit difficult. So I'm adding this to the task, to the slide number 3. So we're adding the angle here, and then how to print it out. So you have a couple of options. So one option is the following way. So the angle could be plus string, and we convert the angle to the string. So we can write it in multiple lines. So angle player get angle, and then convert this to the string and add it to the string here, right? This is one option how to write it. Another option that is a little bit nicer is to use the f strings that I already have given the example. So then you even don't need to call this part, but just write it in this way. In Python, you can write these things in many ways, and it works regardless of the way how you write it. In most cases, so sometimes there are some code style that should be used to like make the code easier to debug. Generally, you have options. So now if I run it, let's see if it works. I added, by the way, these lines to the Jamboard if somebody wants to catch it up. So now it works. So if you run it, it will give you the result that I gave you before. So okay, let's then okay, first of all, let's wait that everybody catch up. So because the previous one was showing that there was not a great compliance in the beginning. So let me show you what I mean here. So I will go to show you the Jamboard as well. So in the Jamboard, slide number 3, we have the code here. So if you need to help to write this, look here. So you have the code here. So that's one. Then the other thing, so now I will write in the chat here. So is task 2.3 okay? Okay now. So can we move on? So plus minus, if any problems, so plus minus problems, right problems. Okay, do I see any comments? No comments yet? Tev izdevās riep? Nu, ir pieejams kaut kā Jamboard arī. Mārtiņš noteikti spēja palīdzēt. Izdevās jums? Abiem diviem, ja? Vai man vajag atnākt palīdzēt kaut ko? So, I see 1 plus. Let's see what happens with everybody else. Okay, I have an opportunity while I'm waiting to research a little bit regarding the situation with the static classes, static variables, sorry. Jā, mums pārējie visi ir online. Mums vienīgais tie datori diezgan lēni, bet paldies, ka tur uzinstalējāt tos PyCharm. Tas ir. Jā, ļoti lēni. Jā, bet pagaidām mēs varam iztikt, es nezinu, kas notiek, ja ienāk 10 un mēģināt palaist, bet pagaidām 2 strādā. Tā. Jā, paldies. Jā. Jā. Ok, paldies. Super, paldies mums tūlīt. Tā. Jā, tad mēs kaut kad pārunāsim. Jā. Jā. Labi. So, jā. Es sapratu. I see 2 pluses in the live class here, and I know that some of you also submitted the task, so I hope that we are soon ready to move. So the next, okay, let me check in the class if everything is okay. So start. Okay, let's move on. So the next thing that we have to do is to make that the player is rotating around itself. So to do that, what we need to do is following. So I will open also another task. So let me check where is the angle stuff. So the angle. So we are creating rotation matrix out of the angle. So we are feeding in that function rotation matrix the angle, and we are generating the rotation matrix that later we dot product with the vector of the geometry. So this line in Latvian means scalarā matrica rezināšana, or that happens in this part, but before we need to calculate rotation matrix. So rotation matrix is like a transformation for the vector around some angle. In this case, it will be around z-axis with some angle. So if we go here in top, there is the rotation matrix now at this moment is 0 here, it seems like. So let me see if everything is correct here actually. So set angle. Then we are doing the rotation matrix. Then we have the vector here. Okay, so let's add a few lines. Let's add a few lines, I think. So set angle, vector, update transformation. Update transform. Okay, sorry. Yeah, thank you, thank you. If I'm starting to tell something and you don't see it, please let me know. It's a good that I have people in the class in person so they can help me out to say. So here the idea is that we set the angle, then we generate rotation matrix that we store in our value, then we modify that value by using the dot product. So the dot product is the matrix scalar multiplication with another vector. And what we get out of this is the vector that is rotated around z-axis by some angle. So we will understand step by step how this works, but let's first implement then the rotation matrix. And to make sure that it's actually working, let's do some other things here. So here, the update transformation. So update transformation. So let's then set the self C. So this will be the combined transformation. In this case, we will copy that from or let's say copy from the self R. So this is rotation matrix copied here. Then we also will copy this part of the code from 75 till 77 lines. Unfortunately, I forgot to copy it myself in here. So let's do it here. So what we need here is to change the vec2d to vec3d like that. Then we need to dot product with the C matrix, the combined matrix, and then we need to convert it back to vec2d. So you have only two very small changes here. In the lines 89 or 90 and in hundreds lines here. I will add those lines to the Jamboard now. So they will be on the Jamboard as well. So you literally have to add now 4 lines of code. 4 lines of code. Here these lines and this line. So that will make sure that the rotation matrix should work. But the rotation matrix itself is not implemented. So if I run this code now, what it will create is probably mayhem. It will just it will not render the spaceship at all, or it actually is. So if I change the angle, immediately the spaceship disappears because the rotation matrix is wrong now. So the all of this introduction is for that you need to implement rotation matrix yourself. So now I'm opening the task 2.4. And I will show you how the rotation matrix looks like and what you need to do. So let me show you what you need to do. So you need to add these 4 lines of code. Then you need to go top here in this function from line 14 to line 17. You need to change this function, only this function. And then you need to submit the code in the Google Classroom. And again, if you don't understand how to do this, or you're trying to do this and something is not working, please submit the code as you can. So if there is something not working, just submit the non-working part of the code rather than not submit anything at all. Please do that. So what you need to do is following. So let me go to the Jamboard. So first of all, add these lines. So in the update transformation function, add the copy of the rotation matrix into combined matrix. Then also add these 3 lines very carefully that you convert the geometry vector 2D to the geometry vector 3D. Then do the matrix scalar multiplication. Then return back to the 2D. And then append them for the drawing of the spaceship. Afterwards, please implement next the rotation matrix function. So what you need to do, I will try to make it as simple as possible. So you need to implement this inside this function. This is deliberately that I'm showing you the equations that you need to implement, because every lection that we will have more and more equations that you need to implement yourself in Numpy. So it's all about the equations. So here you need to implement this matrix. So this is actually the rotation matrix, and dot product is actually this. And when you do the dot product with position, you will rotate this position around z-axis using the angle theta. So let me annotate this a little bit more to make it absolutely clear what you need to be doing now. So let me see, where is this thing? So okay, let me see. So by the way, the code is now up in the Google Classroom. So the Google Classroom, we have the task 2.4, task 2.4. And here, the rotation matrix is this part. So this is the rotation matrix part, the red one. And just to explain what's else here happening is, let me write down actually exactly from the code, what you have in the code. So this is from the code, if I go and look in the lines. So this is vec3d, so this part is vec3d after transformation, after dot product. And this middle part is actually stored inside cell R, right? And it is changing depending on the angle, of course. And then this part is the vec3d of each position of geometry, self-geometry. So I really hope that this is clear. So the idea is that you need to implement as a Numpy matrix just this part, just the red part. Please do that. Also, just to make sure that this is clear. So this is in the slide number 4, and now let me write down, is task 2.4 clear? Should I explain something more? Should I explain something more here? So the goal is now that if you implement this matrix, you will see that that the spaceship starts rotating around itself. So that is the goal here. So my question is here in the Google Classroom. Yes, thank you for this for comment. People in students in so yeah, if you see that I'm talking and something is not shared, let me know. But now I have the question regarding task 2.4. The task 2.4 is open now. The previous task was submitted only by 3 people, but hopefully the others catch it up. So more, please, more information. Okay. So let's try to explain more. Okay, so you have in the Google, in the Jamboard, you have this part that should be looked at. And now let's try to explain more. So first of all, implement these lines. So these lines are, you actually, at this moment, maybe you don't need to completely understand them. So the first thing is what we're doing here in this line is copying rotation matrix as combined matrix, because later we will add more transformations here. Later we will add more transformations here. So that is the reason why we're doing this line. So then with these lines, so only way, so this is again something you will catch in the next task, but it's just that I want to show you first why it matters. So first, you can multiply or do the dot product, basically dot product only with basically equal either it's like so either it's the row or column dimension depending on how it's transposed. So I would say the equal number of rows only with equal size matrices and vectors. You will see that there are options how to change the size, but in this case, if the rotation matrix is 3 by 3, so rotation matrix is 3 by 3, right? So the shape is actually 3 by 3, right? So it can be dot product only with something that is basically 3 by 1 or something like 3 like that. So that is vector, that is just the same size. I cannot multiply by that matrix something that is two-dimensional. That's why I need to change it from two-dimensional to three-dimensional. And the change actually is very, very simple. If we go in this code, we see that we actually create just the same as we had in 2 dimensions and adding 1 here, or when we create it from 3 to 2D, we're just removing the last dimension. This is like very, very, very simple. So that part. Then for drawing it back on the screen, I'm changing back to 2D, but actually I even don't need that part. I can just like do it in this. This will be exactly working fine. So this will be working fine as well. It's just that I would like to wanted to have it in 2 dimensions, but it works fine also like that. So I hope this part is clear. And then here, when we set the angle, we are generating new rotation matrix. What we need to do is to construct this rotation matrix inside this function. So now what we have here is actually zero matrices, so 3 by 3 size. So this what it means is generate please me 3 by 3 zero matrix. So what it looks like is following. So MP array, and we have 0 0 0 comma 0 0 0. So this line does this thing here. So this is really simple task. Please generate me the rotation matrix with the equation that I gave you in the Jamboard and also in the task, and make sure that the spaceship rotates around itself. I hope that now the task is clearer. If it's still not clear, then you need to ask me a little bit more specific questions. What should I explain? Otherwise, I cannot explain without knowing what needs to be explained. So now I'm sharing back to Jamboard. So please do the code. Let's see who does do it first. So right now, nobody has yet submitted the code. Meanwhile, I will double check that everything is working fine, so that I don't have mistakes myself. So and if I have time, I will also still keep looking about those static variables, because that is fascinating. Okay, it's working for me perfectly. So if you implement that equation correctly, you should get nicely rotating spaceship. Everything that we are doing now, this is like requirements to be able to do deep learning in the next sessions. This is called, all of these transformations regarding the vectors and matrices, this is linear algebra that you usually learn in mathematics classes. And this is something that must be understood perfectly before we move on. So let me see. So I hope I helped. I hope I helped. Let's see what emotion could I give there. Anyways. Okay, let's see. We have not yet anyone submitted. I will try to help out in the class as well, in the person. Just let me try to look at once again regarding those static variables. I think I got it, how the static variables work in Python. There is one specific behavior that I was not aware before. It's really funny, but I will not distract you now. I will maybe at the end or beginning next time show you examples how to not do the classes. So the way how the students wrote the classes, this is definitely not good way to write the classes. It worked as expected, but it might produce a lot of problems if, at some point. Once again, Python has caveats that actually have a huge number of examples that I can give you where the Python works counterintuitively. But we don't have anything better for mathematics right now. Okay, I'll let you struggle with this a little bit and then help out. So I will add to the Jamboard the example that I just coded. I will also make that on the screen. It seems like that some didn't still get how to construct the matrix. Okay, where is the Jamboard here? So this is the way how you write the matrices in Numpy. So this is the matrix here. This is 3 by 3 matrix with zeros, but what we need is not with zeros, but we need this matrix, right? Also make sure that you have converted the angle from degrees to radians. So convert deg to radians. Otherwise the cosine and sine functions do not work correctly. So it should be quite obvious now. So, okay, we still don't have anyone submitted the code. Let's see in the stream. Okay, okay, let's do another question. Is anyone working on it, or should I show how to do it? Plus, minus. I mean, like working, or give up, gave up. So let me know in the chat here. Otherwise, like I'm just waiting and nobody's doing it. So that's also not cool. I don't see any response in the chat. Hopefully you're not sleeping. Okay. Is it somehow done? Okay, let me see. Okay. Is it somehow done with the for loops? Okay, thank you for the comments. That helps. Also, like if you just like submit something that's not working, also would help. Yeah, I see one person submitted something. Let's see. So Liga. What we have there. Great, excellent. Liga did it correctly. Of course, the code is not optimal, but that's excellent. So I will show what to do and try to explain and try to make sure that you get it and you can do it yourself. But anyways, like Liga gets a cookie, Liga. So that's a good job. Okay. So we have this one. Okay, so here you have it. Yeah, let's then code it together for the rest of us. Maybe it's like just need to connect in your brain some of these things that we have seen so far. So first, this is the matrix we need to come up with, right? Let's see then in the Jamboard we see that we have cosine and sinus values, right? Then first of all we have degrees. So theta should be then converted from NP radians degrees. So it should change this from the degrees to the radians. That's one part. Then the other part is that we have cosine and sinus values, right? So then we can make maybe some C. This will be NP cosine. That will be the theta. So we are pre-computing this because we are reusing the same value multiple times. So on sinus like that, right? So far so good. Then we need to put these values inside that matrix. So first we set it C here, right? Then we have set it minus S here. Then we set C here and S here, and then we set 1 here. Or it could be also like that. I think it will work. So let me zoom in more. And if I run it, I just need to double check if it's actually working, if there is no bug. So I can actually turn the spaceship very nicely. Okay, I will wait for you to catch up with this task. And if now looking at this code you see something that was contradictory to how you think about this code, then maybe you have some question rising, then you can please type that question in the Google Classroom so I can help you out. So okay, so is task 2.4 clear and working now? Now is spaceship turning? If not clear or error, please write a comment. Okay, jums skatoties uz šito paliek skaidrs, Mārtiņ, vismaz? Okay. Okay, nu labi, pagaidīsim. Tā. Galvenais saprast to, kā to pierakstīt. So I have a question in the Google Classroom. Those of you joining online, please try to do this on your code and then respond, or if it's still not clear, then please also respond. What's it? Not turning for me. Yeah, somebody have for one person it's turning, for other not turning. So my advice for Elena, please submit your code in the classroom. Please please submit your code in task 2.4 so I can check it now. That is the advantage of attending these sessions live. I can help you out immediately, so please submit the code. That is one way how we can help out to proceed. So I see in the 2.4 task only Liga's submission. And I see in the chat that at least one more person is succeeding with this. Okay, let's check what we have in the classroom. So also we'll check what we have submitted so far. Okay, so some person is saying that it's turning and submitted, so that's perfect. Okay, I see Ellie in the code. That's great. So we will have bug fixing now. Let's see. So that is also one way of helping each other out. So okay, the temporary code. Okay, here, right. So that's how far she get. Let's see what's wrong with this code. If she says that it's not turning, so here we see the problem. So actually, if you use the pie chart, it gives you different color for variable that is not used. So you see that the vec3d is not used at all. It's not rendered at all here. So instead, you have two options: either uncomment this line or change this here to 3D. So you have two options, and after changing this to like uncommenting this line, hopefully if the equation is correct, then you should be able to turn your spaceship. I will see. So okay, but it's not turning, so there is something else missing. This was bug number 1 here, so let's see what other bugs you have. So then the rotation angle. Okay, I think maybe it's working, it's just that my backend is not the correct one, so let me run it again. Yeah, it is working, so there is no other bug. So that was just the one bug that you had to either use this line or delete this line and then use here 3D. So it's either way it will work. Hopefully I help you out with this one. Okay, let me see in so I see multiple people succeeding with this, hopefully. Okay, that's good, we got so far. So then let's move to the next part that is super critical part for this course and for the linear algebra here. So we need to talk about the dot product. So you see that in the code that I showed you, there was the mysterious line of matrix multiplication, the dot product, where we multiplied the matrix with the vector and we got the changed vector using that transformation. And you see how useful it is, because we can use that matrix and modify those vectors around some axis with an angle. So that is really good property. But in order for that dot product to work, you understand how it works. And the way how it works is, so I will show you step-by-step examples, ask you some questions, and hopefully you can provide me at least some of the answers. So, and afterwards, hopefully also when you implement it, you will understand it. You should be able to understand it. So the dot product, the matrix scalar multiplication, is extremely simple algorithm. So it's actually a function, but at the same time, it's kind of like an algorithm. So it's like very simple algorithm. So here we have two vectors. So it's actually the dot product works always by 2 dimensions. So if we think about it, so we have two vectors here. When we want to do the dot product between those vectors, I will go step by step and try to explain what's happening there. No worries. By the way, I had some better images. Where is my better images? Okay, no worries, no worries. Let's go step by step. Okay. So the operation works like this, and we will examine it a little bit in detail. So it's nothing else than multiplication and addition. So the dot product is just very simple algorithm for dot product is multiplication and addition. There is no other mathematical operations inside this function. So how it works is, so you have very simple way to explaining it. So actually I should write it in a more generic form, but you have here this value multiplied by this value, then this value multiplied by this value multiplied by this value, and then when you have the multiplications of these pairs, you sum all of them together, and then you get the one scalar value here. And this is the case when we have this specific shape here. So the shape, it might be misleading. You think that this is a vector, but it's actually, in the Numpy, it would be more defined, most likely defined as a 2D vector, 2D matrix. Because if you think about it, so this one, what it is the shape of this one is 3. So the shape is, yeah, so this shape could be 3, 1. So we have 3 rows and 1 column. So this is the shape. So V shape. You actually can write exactly the same code yourself in Numpy, and it will give you that shape. Of course, it depends on like a little bit of how it's written, but still. So 1 and 3. This actually was U shape, and that one is V shape. U shape. And the interesting thing is that result shape is 1 by 1. So it means that we can execute this operation only if the column size matches the row size here. So very important to see that this dimension match. So this dimension match this dimension. So if they are not matching, we cannot execute this operation actually. But let's do this step by step. So again, if you're just thinking about this very simple example, okay? So is it clear so far that you multiply this by this, then you multiply this value by this value, then you multiply this value by this value, then you get result here, right? Then for that one, you get result here, right? And for the first one, you get result here. So is it clear so far? The algorithm itself. So if I give you another vector like that, will you be able to calculate the output, right? 2 vectors and you can calculate the output. So this is the matrix scalar reiznašana dot product with the vectors, but we will go step by step, no worries. So then the next question, let me find you another example. So what will be the output of the dot product for this example? So let me write down. So if I'm asking you to create the dot product of this one, so let me try to find where's my LaTeX. So you will write down the question. So you see dot the what it is. LaTeX it. So okay. Okay, so can I copy it as PNG? Okay, so my question is following. So I will for the second equation here. So yeah, so in the classroom right now in person, Martin is saying that the dimensions are not matching, and this is correct. You cannot do this. So this is again one example of saying about why it's important to check dimensions and understand that basically you must match this one dimension must be matching. And basically you're right. Like if we try to write it down, it will look like this. And you will see that we are missing one variable here. So we are trying to do the same algorithm step by step, right? And then we have a serious problem here because we have one variable here, but we don't have anything here, right? So we cannot execute it. So it's really important to understand how this works so far. Okay, so great. Martin's answered correctly. So that works fine. So then let's move to the next part. So now let's think about making the matrix multiplication using the vectors. So I mean the vectors, but with multiple vectors. So let's see. So there was a very nice example in a very generic form. Okay, let's start by generic form, and then let's make it actual example. So in this case, there will be very simple multiplication with the two-dimensional matrices. So the generic form looks like this. And what we need to notice here is very simple thing. So this is actually exactly the same thing that you just saw in the previous slide, but just written in this form. There's nothing more difficult than this part. So what's happening here is following. So the vector that you saw in previous slide, so here you have one vector that's called R1, right? Then you have another vector that is called C1, right? And then when you have the dot product between those two vectors, you put that value here in the resulting matrix, right? Is it clear so far? So previous slide where we had like two vectors giving us one scalar value. Here we have a matrix of multiple vectors with different orientations. And when we do the same thing, we put that scalar value in that exact row. So that should hopefully is at least some far clear. So that's what we have there. Let's look more of some examples. Let me see, find maybe step by step some example. Okay, let's look some step by step example. Okay, so let's add some values. Let's add some values. By the way, the output in this case will be again 4x4 matrix, but depending on these two shapes, we can also get output in different shape, and we will look at that as well, hopefully. So let's see. So we have an exact example. By the way, I'm showing all of this, and you should try to understand it as hard as possible because you will also need to implement that in the Python. So here, let's see. So if we have then the question that we need to answer, what are those four values here in this matrix? So let's add here some question marks. So this will be the red one, question mark. And then we will have, well, also the, let's say, green one. And we also need to calculate here the yellow one and the blue one. So we need to calculate those 4 values here. So it should not be that difficult to do. So let's ask the question first. So what is the red value here? Um, uh, so remember that you have to multiply them by pairs. Like, so you multiply one pair plus another pair. So that's kind of, it's not like exactly just one value, but hopefully you didn't hear exactly your answer. So okay, let's see. So R1. So we have the R1 by the C1. So what? So there is R1 dot C1, right? What's in that is that we multiply 1 by 5 plus 2 by 7. So then we have on that side 5 plus 14, right? And then we have 19, right? So that's the answer for the red one, right? So let's do then in the chat the question red, green, orange, blue. So let's see. So what is the red, so green, orange, blue values? So either, yeah, so I guess that would be the easiest way to write down the answer rather than writing the matrix form in the, like in this line here. But please calculate those values manually and type in. The zero will do that in a minute automatically using the basically the coding template. Okay, let's see. So this is on the Jamboard slide number 6, and here is the question. Okay, basically the operation is super simple, but if there is something not clear, you can write here in the comment what is exactly not clear, and I can try to explain you. Okay, see one answer here in the chat. You see two answers. Let's see if we have any differences in the answers. Okay, nicely, Martins is also giving explanation even. So it's very hard then to argue if you give exact explanation how you get to that point. But it seems like it's correct. So yeah, at least those three people seems to have correct answers. 3 by 5, 4 by 7. Right. That is good. So I'm happy that some of you are already capable of doing that. Okay, so by the way, if somebody don't know how to get the other value variables, Martin's posted the answer in the chat. Okay, so we just need to look the last example with the matrix multiplication before starting to code this, because there is another option that you can do with these matrices that is very useful to understand. So let me find the example. So that example is that we can change the output shape of the matrix as well, because we just need to match the one shape of one dimension of those two matrices to have the output in different dimensions. So let me show you that. So here, and by the way, all of these operations that I'm showing you, they are all the time used in deep learning and artificial intelligence. You cannot escape them at all. So, so here there is the way how you can change the dimension. So if you look at this, let's see where there is the matching dimension. So we have the same number of columns here, the same number of rows here. So, and as long as those two match, we can get output in the shape where we will have the output will be in this shape by this shape. So really nice. So that using this property, we just can change the dimensions of the vectors. So what it actually means is that we can project something that has high dimensions to very low dimensions. So if we had like, let's say, the 100-dimension vector, we can then project it down to 3 dimensions or 2 dimensions using the same property. So if you look carefully here, what we have here is again the vector, right? So this is the same shape as this shape, right? So we can do the dot product without any problem, get the value here, and so on for all of the others, right? And we get this out. So is this clear, right? Or not really? So this is exactly the same equation as before. No, nothing changed at all. The only difference is that we changed the shapes a little bit and got this mathematical property where we can change the resulting shape. So there is the big requirement for this to work is following. So let me write it in text. So the rows, so A matrix rows, calls must match the B matrix rows. So those shapes. And remember, for the Numpy arrays, if I generate the matrix in Numpy array, I can use A shape and B shape to get out the shapes. So in this case, A shape will be the 2 by 3, and this shape will be the 3 by 4, and then the resulting shape, result shape, will be actually 2 by 4. So you see that just using exactly the same operation, nothing changed from the previous slides, we can have very interesting property with matrices. Do you get it? Like if I ask you to get those values, I give you the example, like one matrix, another matrix with values, would you be able to calculate the values? Yeah, so this is what the dot product does. So then the very important thing to understand, the dot product always works with last two dimensions. So even if you're using the vector, like if you're multiplying the matrix here with the vector, so what I mean by that is that let's maybe, I should maybe write it somehow. Okay, so if you have this matrix multiplied by a vector that is just the first column, you will get out actually, so just two-dimensional vector here. So let me try to show that example actually. Let me see what was the LaTeX version of writing those matrices. Just a second. And just want to make sure that you understand this correctly, otherwise it will be not good at all. So LaTeX matrix, forgot about the way how you write it. Just a second. Begin matrix, right? The plane matrix, the B matrix. Okay, cool. So I will show you that in the LaTeX how I write it. So let's see. So this is our example. We need to have the full screen on. Just a second. Make sure that nothing is open that is not necessary. So the full screen, this one, sorry, this one, right. So I will try to give you another example. So, okay, let's see. So we have the here the first matrix will be A. And so let me write down. It takes A, right? So this will be actually something like A. So let's 1, 2, 3, 4. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, right? Okay. Oh, sorry. 4, 5, 6. Right. Okay, so this is one matrix. Then the other matrix is the B one, and this is actually then the vector. So this is really interesting to think about it. So let's see. So there we'll have the 7, 8, 9. So let's see how it looks like. So like that. Maybe I'll add it actually like this. So now we have these two matrices. So then if I do the AC dot B, right? So what will be the output of a shape here? So just a second, there's a bug. Would be like that. So I will copy this as a PNG, add it here. So let's just to make sure that everybody understands. So my question is actually following. So A shape, B shape, and R shape, result shape. What are those values? So that will be my question in the chat. It's actually not, the shape is not the answer for this this problem. It's just the size of the matrix. What will be the size of the matrix for all three of those shapes? So I'm posting it here. And if you don't understand at all what I'm saying, then maybe ask exactly, like at least some small part of what you understand. Where is the question? I can help you out. So I'm having this question in the chat now. So what will be the shape? So to help you out, I will start giving the first shape. So the first shape is 2 rows, 3 columns. Always the rows are first. Rows, columns. So that is the way how all of the mathematical matrices work. So let me see, do you have any answers? No answers. So to answer this question, this is not a guessing question. You need to go back to the previous one, look at this, how it's constructed. And if it's not clear with this one, then go one step back, look at this, see how this is constructed. If it's still not clear, look at this. So basically, we have very, very simple algorithm how to get the new result here. And my question is, what will be the dimensions of that new result, or in other words, shape? The shape means dimensions. So if you write in Numpy code, the shape, it will have the same thing. Like you define NP array, whatever, and then write the next line, that means a.shape, and it will give you this result. If somebody don't understand it, or like there's some, like want to code it, you can even try to write this as a code, and then execute the dot product and see the result and think about it. Okay, I see that I have some answers, so that's nice. So we have one answer from Liga. So I will not say if it's correct or not correct. I want to wait for more answers. And Liga could also try to calculate the value herself, like what is the output that would be useful to calculate that output as well. And afterwards, when we will do this task, you will see that we already are using the same property in our game already. I have only one, I have another answer as well. I have three answers. All of them agree on the same output, and the result is correct, of course. So again, if we think about it, so the output will be two-dimensional vector or matrix. So it will be vector basically, but it's like a transposed vector, and that's why it's a matrix. So let me find where is my LaTeX. Let me try to write it down then. So the output is following. So this will be the output. So A and B begin. So here we'll have the two-dimensional output, and that now of course we need to calculate these pairs. So it's all about calculating pairs. So we are multiplying this by, so the first one we are multiplying by the second one. Then we are plussing that to the second one, 2 multiplied by 8, right? Then we are plussing that by 3 multiplied by 9. That's very easy, the first one, right? So the second one, almost everything stays the same except the one line changes. So that there is instead of 1, there we have 4. Instead of 2, we have 5. And instead of 3, we have 6, right? So that is what we have here. So let me LaTeX it. Okay, like that. And if we calculate then the output, we will get just a two-dimensional matrix here, right? So let me add it actually here. And what has actually happened here, which is very important to understand, is following. So that the here we had a three-dimensional vector. We have in the code as well. So 3D vector, so vec 3D. And then we applied some transformation. So this is a transformation matrix. It could be rotation or identity or scaling or transformation or anything else. So this is just like a one rotation matrix for one transformation matrix. But this transformation matrix, what it does, it projects through three-dimensional vector as a two-dimensional vector. So then we get out the result as vec2d. So what happens is that we can project. You can imagine that instead of three-dimensional vector, that here we could have 128-dimensional vector, and then we can project it to 2 dimensions. So why it's useful is that you can imagine you have sensor readings of a robot that have like 128 sensors, and then you project all of those readings in a very nice plot in a one point. And then you have like some new state, robot goes to another corner, and again new sensor readings, you have again projection on as a one point. And then we can compare how different are both of those two readings, you know? So that's very useful. So let's then go back to the code here. So I will give you now the task, and you will try to implement that yourself. So this will be the task 2.5. So the 2.5 task assign. So that is opening now, and you will have to implement this algorithm, but no worries, I will give you also the template. So where is my template? Dot product template. So here is already a template for you given, and also it is given even the example. So if you look at this template, in the bottom part we are printing out the values from the Numpy dot product and from your dot product, and those values should match, right? So if it's correct. So then also this dot product function, you don't need to care actually about all of the things around here. By the way, yeah, so you'd only care about this middle part. So the middle part, what is actually happening here is that we are creating the result product, the result matrix here, that is from the rows and columns. So it outputs the X rows, so the first matrix rows and second matrix columns. So output as shape first matrix rows, comma second columns, right? And now you need to implement to fill these values inside product. So how to fill values in the product is following. So in Python, if you have two-dimensional matrix, you can fill the values like this. You say, if I want to fill the 0.0 value with some kind of value, I do like this. If I add a breakpoint here and I will look what's happening here, you will see that. So I'm trying to run it. So what we have here is following. So the first matrix looks like this, the second matrix looks like this, and then the result should look like this. But now the result should be two-dimensional, right? Very simple actually. And we just put value of 1 inside the cell 0, 0, right here. If you want to put value in the other cell, we just use the, so the first one is rows, so the rows we have only 1 in the second column. So let's add the second column as 2. Let's run it again and see what happens. So the product, see, you see 1 and 2, right? And so you need to implement that algorithm that I just explained. So how to do that is following. So we need to set each cell a specific value. So how I will help you out with the very beginning. So because I feel that it might be difficult for this class, but I will try to do as much best as I can. So here then in the range, so we're going by the first, let's go by the rows, I guess. So let's see, rows I think would be good to start. So yeah, so the rows of the Y rows, I would say. It doesn't matter actually. You can write it as you want. It's as you see that the changes that the algorithm can be implemented a little bit different depending on how you want to implement. So let's go the X rows and Y columns. X rows. The code template is available in Google Classroom now. So then the Y columns, right? So you go like that. Then I suggest that you either have an additional loop here, because if you don't have additional loop here, then you need to know Numpy a little bit better. But I suspect that you don't know Numpy that good to make this without additional row. So additional row would mean that you will have here the Y rows like that. And then what you will have to do yourself is to fill this equation. So you need to change this part. So to do something here, so change this line. So this is only thing that you need to do. I already give you everything. So you need to just change that one line to implement that algorithm. And if you implement that one line, you will get the same results as a real dot product. So I also know that most likely you will not be able to do this right now, so I will leave this as a homework for later, and we will proceed with other things, because in general you understood how this works. You just need to go to the details making it work yourself, because it's quite very important to understand how this works, otherwise we will have big problems later. So okay, let's go back to the game then. Okay, and let's implement then the other thing of changing the shape of the vectors here without manual hacking of the code, but using the dot product and the addition functions. So now I will open also the task 2.6. So this will be task you can do by following the code that I show you now. So later at home, you should change this to your own function. Change this to your own dot product. But now let's use Numpy product, no worries. And now I will try to show you how to change these vectors using the dot product. So this is exactly what we did on the Jamboard. We trying to project from 3 dimensions to 2 dimensions. For example, in this part. So let's say, so we will have identity matrix here. So identity matrix, I think I didn't tell you about identity matrix, so let me go back and explain one more interesting thing. So this is really dumb, very interesting. Like it's actually not so I even didn't explain it because it's so simple. But let me show you, so no worries. So we often use identity matrix also for a couple of operations. So let me show you how the identity matrix looks like. So the identity matrix looks like this. So if you use the dot product, you will see a very interesting thing. And actually you can see it even in 1-by-1 identity matrix. If you multiply something by identity matrix, so if you have, let's say, resulting matrix A matrix by dot I is the identity matrix, right? If you use it in the first line, anything you multiply by 1, you will get out the same thing, right? So if you do the same in multiple dimensions, like in 2-by-2 or 3-by-3 or whatever, you always will get the same value out. So that is how it works. The one useful thing is if we change the shape of this identity matrix, for example, we cut out only this part, or maybe this part, the other part, right? So in that way, okay, sorry, this is, what are you doing? So if we cut out these parts, we can change the dimensions, right? Without changing the contents. So if I cut out this part, or if I cut out the other dimension like this, then if we do the dot product, it will change dimension without modifying first dimension's values. So it means that we can use this to project something. The other property for the identity matrix that is commonly used is inverse. So let me try to show you what it is. So if I have some matrix that is C dot, I will show you in a second, by an inverse of that matrix, I will get the identity matrix. So let me add it, copy PNG. So the other mathematical property is this. And this is also useful. So if you want to check if some transformation or vector or is like in other direction. So you have one vector that is in this direction, and then you have another vector in that direction. If they are absolutely precisely on the same like line, or this transformation is absolutely perfect, then we will get out this kind of matrix. So this is again very useful mathematical property, and we will again use it just in a second. So, and I will show you how to do it. You just need to then submit the code when it's ready for you. So now remember that you have the homework for the dot product, but now let's move back to the code here. We'll try to explain how to do this. So so this will be the identity matrix. We want to change it from the 3D to the 2D, NP array, like that. Like that. So just don't want to mess up dimension. I think the first one was the rows and second one was the columns. But of course, you can do this by experimentation, but I don't want to do this. So yeah, so the columns and rows. So first of all, so here we'll have the 1, 0, 0. So this should be from 3 dimensions to 2 dimensions, and then 0, 0, 1, 0, 1, 0. Okay. This, if that would be a full identity matrix, there would be an extra row here, but we can use it as it is now. So that part, and now if we project this using dot product, so I am projecting 3-dimensional vector to 2-dimensional like space using this very simple equation. Now I'm getting out 2-dimensional vector that is cutting out extra dimension without changing the contents of the dimension. So now the same thing with increasing dimension. By the way, in deep learning, this kind of equation is super common. Like you do this all the time. You change the dimensions, either increasing them or decreasing them. So here in this case, we have the same thing in opposite direction. So 0 and 0, 0. And now we do again the projection. So we are projecting from 2 dimensions to 3 dimensions. So that is great. The only problem with this one is that it generates out the output as the vec to the x, so the first dimension, and the vec to the second dimension, and 0. But in order for the transformations to work correctly in 3 dimensions, if we were, for example, rotating around z-axis, we need here 1. So, and to do this mathematically without hacking using the code, we can just add the vectors. So np array, adding this vector like that. And now it should work exactly the same way as before. I will check it if there is no bugs. Yeah, so I can rotate successfully this spaceship using these equations. So yeah, so either you can stick with the code that I had before, or you should change it to this code, because that is also a task. And let's then move to another task. So I know that we don't have a huge amount of time left, so that's why Okay, but regarding this one, let's stop with this one. So I will add. I actually will write that in the as a question. So is it clear how this works, and can you do it yourself? So this task is number. So which one was it? So this is 2.6. So is task 2.6 clear, and you can do it yourself. Basically, you just need to copy my code, but is it clear what is happening there? And if it's not clear, if not clear, then please write what is not clear. If not clear, then write what is not clear. Meanwhile, I will I will maybe add this one on the Jamboard, just in case. So you should be able to do that. So actually, I would probably add. Okay, I will add that. So, anyways, you still have to do something yourself. I don't like giving out too much of without that you don't need to do yourself anything. So I'm adding that to the Jamboard. And let's look at the chat here. So I don't see any answers to this question. Meanwhile, I will check if my calculations for the positions are okay. We don't have them yet. Okay, let's wait for some responses that you're done with this very small task, and then let's move trying to make the spaceship fly around. Yeah. Okay, I don't see answers here, which is not really encouraging, but I hope that at least you're still tracking. Okay. Anyways, we need to proceed, so you can later catch up with this small path. I really hope that you can, because so far, like all of the things that I showed you so far, they are like very basic things, step by step, becoming much more difficult. But in a sense that there's nothing so difficult that you cannot do it with the hand on the paper. So you just need to learn how to code that in Numpy. And of course, it will take maybe a little bit of time if you're not familiar with that. So, okay, let's then code the moving of the spaceship around the scene here. So to do that, first of all, we need to update the position of the player. So to update the position of the player, what we should do is to go to the update movement here. So, and it's using actually the same method as normal computer games does. It uses the delta time, so that if your computer is faster than other people's computer, it will not be different speed. So we will always use the delta time. So here then there is the vec position. So this is a position of a player or some other movable object. And we will change this position by the self vec direction. So we have some direction on which we are going. And we will multiply this by the self speed. So the speed, so we'll give the length of that vector. By the way, in the beginning, the speed is 0 now. The speed is 0. Let me check. Yes, the speed is 0. And actually, I don't think I see the some kind, or just a second. So I have the function activate thrusters. Yes. So we will implement also the function activate thrusters. So because the speed is 0, the spaceship will not move. Of course, we need to give the speed. So then there is the multiplied by delta time. So if we multiply by delta time, we make sure that this line of code works exactly the same way if you have slow computer or fast computer. So it will move the same amount of distance. So I will add this one line of change inside the Jamboard. So this is changing the position of the player depending on the player's direction and also depending on the speed. And of course the time, but the time is something that we do not affect here. So that's part. Then inside the player, we have the activate thrusters. So let's add some speed here. So self speed. Let's see. So how much should we add speed? Maybe I should check. So I think 50 would work, but I'm actually not super sure about that. Let me check. What is the delta time? In this case, E-3. I hope it will be okay. Maybe if it's too fast, we can reduce the speed. So that part, and also we need to decay the speed. So we don't want that we always press the space bar and it becomes faster, faster, faster without reducing the speed. There is no friction. So if it would be like absolute space, probably would be no friction, but still. So then here we can use the property of object-oriented programming that we discussed last time a lot. So we are rewriting or overriding the superclass function. So update movement by dt, and we are reducing the speed every frame we are experiencing the game. So let's see how we will reduce the speed. Let me see, let me think. So let's reduce it by 10. Okay, so actually we could write it even, it doesn't matter, we can write it here. So self speed minus dt times 10. Also, we don't want that spaceship flies in the opposite direction, so we need to make sure that speed is not below 0. So one way to do this is self speed is maximum value either 0 or self speed. Or another way how to write exactly same line would be if self speed is lower than 0, then we set self speed to 0. So this is exactly the same line there. So we are decaying the speed over time. So these are, what is happening here is that the player is getting the extra thrust, so this getting the forward motion when we press the space bar, and then if we are not pressing the space bar, it slowly becomes slower. So that's what's happening here. Of course, it's still not yet working because we are missing key pieces. We don't have translation matrix, and we don't have any way to generate translation matrix. I'm adding these parts of the codes in the Jamboard slide number 10. So they are added, what I just did. Now, if I go to update transformation, so now it becomes interesting. So it's again using the property of the dot products. So let's create a translation matrix. So do we have translation matrix in the? So it's not actually there, but we could add it actually. So translation matrix, T is translation matrix, dx, dy. So self, vec position x position, and self vec position y position. So we have two positions here. And we have two matrices here now. We have the rotation matrix and we have the translation matrix. So now we just need to dot product them in the correct order to make it fly in the correct direction. So let's see. So the first one should be then the I think it should be translation matrix. The best way probably to make it a little bit simpler would be to create C as identity. Oh, it already is C as identity, so that's great. So then we can write it self C is the dot with the translation by self C, except the self C should also be, oh no, the first one should be rotation actually, and also we could not do that. So okay, let's drop it. So self rotation and T. Okay, so that will be fine. Okay, so we are multiplying together two transformations. So what is happening here is combining rotation and translation into single transformation matrix that we can then apply to the vectors, and we don't need to do two separate transformations. We can do just once. That's very useful. Okay, so we can do that. So that's great. Okay, let's see if hopefully that order is correct. I will drop it into the Jamboard. And then the last thing that's missing here is that we need to implement translation matrix, and I want you to do this now because at least this part you already did it once, so you should be able to do this very simply because you already did this once. So you did this with the rotation matrix. Now you will have another matrix very similar, even simpler than rotation matrix, that you need to implement in order for spaceship to start flying around. So let me show you how it looks like. So this more simple task looks like this. So let me find you the Jamboard. So the matrix looks like this. And this is translation matrix. You need to implement translation function, and you need to add this one. So I believe you can do this. This is more simpler than previous task. So this is now the task number 2.7, if I'm not mistaken. So, and I will show you where you need to write actually, and what you need to submit. So now you have translation matrix here, right? So it's zeros 3 by 3. You already know how to make it, right? You just use it here the same way as it was for the rotation matrix. And if you implement correctly, then you should have spaceship flying. So this is the task for now, today and right now. So the other tasks, I understand that it might take you a little bit of time to get used to, for example, to implement dot product. That's why I did not expect that you do this immediately. But this one, you should be able to do this now. So I will try to order around the Jamboard, slide number 11. At least if you're not implemented the previous parts of the code, then at least submit please only this part, so then make sure that you understand this so far. So the other parts are also available in Jamboard in previous slides. Meanwhile, I will check if I don't have any bugs. I will try to implement it myself. Now, okay, I have bug actually. That is a very funny bug. I actually wrote the C in the wrong order. First we need to do the translation, and then we need to do also thing. Yeah, I think that's the correct orders. Let me check. Yeah, I will update Jamboard. There's just bug in one line, so it's not nothing big. So, yeah, so now it's flying very nicely for me. So, but I will add the bug fix, and I will make it with the colors so you understand where it is. So it's a very, very small one. So here. And also, if you make the mistake there, you will see another property with transformations, that if you have them in wrong order, so you will have different result. This is not like a simple multiplication in mathematics. You will always have different output when you are multiplying different matrices. So, like for example, A dot B will give you C, but B dot A will not give you C. There will not be C. So the answer will be different depending on the order in which you do the dot products. So that's why it's important to set in the correct order. So you first want to rotate it actually, and then translate it. In this equation, it seems another way around, but basically it is what it is. So you will have some other transformations that we will add later. You'll see that it's very important to have the correct order of them. Okay, let me see what we have so far. So in the stream, no comments yet. Let's see what we have. No, nobody yet submitted the code. Tur skaidrs, kā to implementēt. That Tx and Ty means delta x and delta y. So how far we need to move from arbitrary position. So you don't, please do not overthink it. So it's just is just the so the tx is dx, this one, that value. So there's nothing complicated here. This is an extremely simple task. If you start overthinking it, maybe you start thinking that you need like move it somewhere around. It's just like very simple matrix implementation, and the dot product does everything for you itself. It changes the position, then it also rotates first it rotates the player, then it changes the position. If we do it another way around, then we rotate all of the road and then change the position. So it's actually interesting. So you have a situation, you have first the player, then when you apply rotation matrix, it like rotates in that direction. And then you apply so it's like I guess in that order. So the T, then it moves to some position here in the same direction, right? But if you have this in other order around, then what happens is that you first rotate the whole row, so your whole screen is like that, and then you move the player exactly like it was here, somewhere here. So it's in the wrong way then, okay? So the order of transformation matrices means the way how you interact with the whole your kind of road or the vector space. So if you have it in the wrong order, then you first turn all of your vector space and then move the object. Or if you have it in the correct order, then you move the object and then you first turn the object and then move it. So it depends on just on the you can experiment. You change it. Understand what I mean. It's very simple to understand this logic. If you will try to change these two around, I will show you in the code. So if you change the T and R around here, you will press the button, you will see that the turning buttons and then the flying. The whole road is rotated. But if you have it in the correct order, then the spaceship is only rotated and it's moved to the correct position without changing the whole road. So that's kind of I think very nice example to show how important is the order. So okay, I see actually the answers. Excellent. So I have two people, both Ligas are submitted the code. That is excellent. So I have correct answer from one Liga, and so which one did I open? Okay, and the other Liga. Also correct answer. Okay, you used even TX, so it doesn't matter like what is the variable name, but if you want to be precise, you can use TX, so that's great. I hope the spaceships are nicely flying for both of you. So I'm happy for that you understand so far this very simple task. So Ligas both receive the cookie. Really good job. Good job. So before we can move to the last part that we need for the homework, but just to make it kind of finishing the game, it will give you simpler version of the homework, not the full version, is that we will need to generate geometry for the planets, right? So I will assign the task. So the task 2.8 will be the algorithm, very simple algorithm. Maybe I will add additional like kind of task for somebody who wants to implement harder algorithm. But basically the algorithm is super simple. You need to generate the circle using the vectors. So for the planet, so we could have the planet. So I will share the screen, Jamboard. So the algorithm is following. So we will have these equations to generate the circle. And this looks like this, basically. Here is a very nice picture. So you're changing the theta angle, and you're having the kind of like a loop, forward loop, where you change the angle from 0 to 360 with some delta, and you generate all along the path vectors. So you generate one vector here, 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 and when you connect all of them vectors in the like correct order in the clockwise manner, you will get very nice like the circle, right, that you can use for your planet to generate the geometry for the planet. You don't code planet, of course, by hand. You use the geometry here. So what I mean by that is like a pseudo code of what you need to do is for theta in if the theta degrees basically is in range from 0 till 360 with some kind of 5-degree step, right? And then you calculate the geometry, right? Back 2D, and this is just the NP array, of course. And in that you add the X and Y values here, right? You add those vectors to the geometry, of course. And here the X is basically the same what you have up here, R, cosinus, and so on. Theta radians, right, so on. Anyways, you should be able to do that. So to generate the planet, and if we will go down in the code, let me just to guide you a little bit more where in the code you need to do this. I think I will make the task simpler for you. I will make in so you don't need to probably implement all of the parts of the game. Just make sure that you can fly through the around the planets, and if you are able to implement gravity, then you can do that. So here we have the player movable element, but we need another movable element, planet. So to do the planet, we will use just the same code. This part of the code for the planet. Okay. It's having a little bit difficulty. Okay, cool. Planet. And I want you to add multiple planets here. So this doesn't matter if it's planet here or whatever. So, and here the geometry originally will be empty. So let's add it. Let's write it step by step. So here will be list geometry. That is again good example why the lists are better than Numpy arrays in some cases, because adding elements to the list is much more simpler than adding element to the Numpy array. So here we have for theta in range of something, whatever, and then here in this part you add the geometry to the planet. Add geom. Okay, what was it? Yeah, geometry. Planet, right. So this part is for the planet, and then of course you need to add planets itself. Add planets here. Okay, that will be one task. So that's cool. Then I will also give you a small task regarding the transformation matrices, because here we are actually missing scaling matrix. So what I want you to do, so you actually have very few tasks, very simple, and then at the end I will add maybe some more difficult, but that is not optional. You don't need to do difficult tasks, just the simple ones. So the simple one will be to implement scaling matrix. And what I want you to do is to squeeze a little bit your spaceship. So let me show you what I mean by that. So I will make a screenshot of that. So I'm running, hopefully I don't have mistakes here. Okay, cool. I don't have mistakes. So you will have to add also scaling matrix. You'll have to add planets and the scaling matrix, and the way how it will look like at the end. is following. So now it's looking like this, but after scaling, I want you to make your spaceship, okay, just a second. I want to make your spaceship not as wide, so please add like a scaling. It doesn't matter exactly what scaling, but it should be not as wide. So this is wide, and this is after scaling. After scaling on y-axis, on x-axis. So that will be another task. So, and you, of course, combining those matrices must work in a way that you still can fly around the planets, not that everything starts to squeeze and all sorts of fly around. So it depends, like you still need to understand the maths behind it. If you don't, then everything will be very chaotic. So that will be a homework, to draw a planet. So basically I can even draw what at the end should look like. So and first I already showed you in the beginning. So basically you have some planets, you can fly around them. I will also add a formula for the gravity. If you want, you can implement that. If not, it will be fine also just doing that. Like whatever you will do, like the collision or like exiting the planes, that all of that will be nice additions, but just do the basics, very, very basics. If you can do very basics, I will be very happy. So that's about it for today. As I said, I will add I already added actually in the classroom. We have the playlist with basic Python tutorials, so you can check that out if you're not familiar enough with Python to do these tasks. And you definitely need to do this, I think, by the next time, because next time we will dive in even in more mathematical stuff. And if you're not able to do the simple things with Python, it will become even harder. So it's very, very simple, very important to go those tutorials if you not feel good with Python. So I also recognize that not everybody of you want to be a deep learning AI scientists. So in that sense, that I will try to make sure that you can pass it, at least the course, with like those 50% or something. So just submit also the code if something is not working. You will also get points. If you don't submit anything, you will not get any points. And if you submit the code that is copied from your colleagues, you will also not get points. And both get 0. So that's about it for today. Hopefully it's challenging.